So most of this lesson is most likely a review of previous things you've learned about trigonometry, and most of the points I have up here are just reviewing things you've learned in the past. I would like to make a point about these last 2 points. If you're following like the standard BC curriculum, you may have not seen this. And so here I have a right triangle, here I have a triangle off to the right here that's not a right triangle. That's a confusing choice of words, but you can see there's a triangle here. It's not right. The height of it, though, can be found by, as it says here, a times the sine of c. So I just want to make sure we're clear about that and how it relates to the next part. Because if that's the height, if I know c, well, the height, this becomes a right triangle here, and the height is opposite to c. And if I know a, that's the hypotenuse in this case, if we think of it as a right triangle. And so notice in this case, I can say the sine of c equals opposite the height over a. And if I solve for h, I get h equals a times the sine of c, which is what we see right here. So that height there is always the same as a times the sine of c. Looking at how this particular triangle is laid up. As well, we can use that to find the area of any triangle, because keep in mind this triangle we see, this triangle ABC is not a right triangle, and the height of a triangle is just height times base divided by 2. And for example, if I look here, I have the base, in this case it's b, and that's the b. The height I said is a times the sine of c, so a times the sine of c, all times a half. And so that equation there, area equals 1/2 AB times the sine of c, is true for any triangle, doesn't need to be a right triangle, where c is an angle, any angle, and A and B are two sides on either side of it, two sides adjacent to it. All right, aside from that though, this is most likely all review all the other points of things you've learned before. So let's do a quick question here. In a right angled triangle ABC, the cosine of A is 3/4. I want to find the sine of A and the tan of A, as well as the measure of angle A. So I'll start by making a quick visual here. It doesn't really matter how I draw this. I'll draw a triangle like this. It says it's a right triangle. And angle A, I can call it anywhere. I'll put angle A right here. I know angle A has a cos of 3/4. Now, let's think what that means. Cosine is adjacent over hypotenuse, which means from this angle, the side adjacent to it, which is like right here, divided by the hypotenuse, which is right here, equals 3/4. There's many possible sides I could have, but the simplest would be if I just call this side at the bottom 3 and I call this 4. Notice it works. If I look at the cosine of A, adjacent over hypotenuse is 3/4. And it doesn't really matter what these exact lengths are. I'm not ever asked to find the lengths. I'm asked to find the sine of A, the tan of A, and the angle. So of all these things, I can find the angle of A right away. So I'll do that right away. If I want to find the angle of A, since I already know the cos of A is 3/4, I can use the inverse cos. So if I know the cos of A is 3/4, I can say that therefore A must equal the inverse cosine of 3/4. And you go to your calculator, make sure it's in degree mode, and you should get about 41.4 degrees. Now, in a bit, I'll mention some other options, but that was nice and quick. There's our first answer. So angle A is, again, about 41.4 degrees. All right, I now want the sine of A. Now, to find the sine of A, although at this point I do know what the sine of A is, but I'm gonna find this. Well, sorry, I do know what angle A is. It's about 41.4 degrees. But I want to point out a way of figuring it out without figuring out that angle first. So let's pretend I don't know that angle A is about 41.4 degrees, because I could have found the sine of A right away. The sine of anything, if I look at this angle, sine is opposite over hypotenuse. So I don't know what that opposite side is. Well, I can use the Pythagorean theorem to figure it out. That opposite side must be the same as the square root of the hypotenuse squared minus the other side squared. And so this must be the same as root 7. And so the sine of the sine of A must be the same as opposite root 7 divided by the hypotenuse, which is 4. And if you go to your calculator and go root 7 divided by 4, you get about 0.661. Keep in mind, you also could go to your calculator and type the sine of 41.4 degrees, which I did round though, and you should get something that's quite close to 0.661. However, what I did here is more accurate, because keep in mind that 41.4 degrees was rounded, whereas here nothing was rounded. This is a more exact answer. And so similarly, I can find the tan of A right now. Tangent is opposite over adjacent. So in this case, from the angle A, the opposite side is root 7, the adjacent side is 3. So it's root 7 over 3, which again, if you calculate that, you get about 0.882. And so without without using that angle of 41.4 degrees for A, I got both of those. As well, though, if I'd found those first, I could go back and I could find that 41.4 in different ways now. I could find the inverse sine. If I typed into my calculator the inverse sine of 0.661, it'll tell me about 41.4 degrees. I could do the same thing for here. If I want the inverse tan of 0.882, it would tell me about 41.4 degrees. Just keep in mind, for all these I'm rounding, so the more exact I am, the better. And if I look at what I have right here, these expressions right here are perfectly exact. That root 7 is an exact value. After that, I'm decimalizing. Lots of options. I hope most of this sounds familiar. All right, here I have a problem in which I want to find the measure of LM, which is the length from here all the way down to here. All right, to the nearest tenth of a centimeter. So if I look at my diagram here, I have many ways I can look at this, but one thing I can figure out fairly soon is the length from K to M. Because if I do that, I can then look at this triangle right here, which is a right triangle. There must be a 90-degree angle here. And once I know one of those sides, I have more information. But let's do this one step at a time. Let's first find the length of KM. So looking at the bottom triangle, 10 is the hypotenuse. And from 63 degrees, the side I'm trying to find, KM, is opposite to 63 degrees. And 10 is a hypotenuse, so I want to find the opposite side. I know the hypotenuse from 63 degrees, and so I want to use the sine ratio. So I'll say the sine of 63 degrees is the same as the side opposite 63 degrees, which is Km, what we're trying to figure out, divided by the hypotenuse, which is 10. And there's a few options. You can multiply both sides by 10, and pretty quickly we get to Km equaling 10 times the sine of 63 degrees, rounded to the nearest several decimal places, because I want to use this to go forwards. I get 8.9. I'm going to write 1 0. I'm going to put 2 zeros after it, just to show that when you do this on your calculator, I'm just pointing out that if I just put 8.91, you may not realize that it's actually very, very close to 8.91. The next two decimals are both a 0. Even better, though, is that the less you round, the better. And even better would be to keep this exact value on your calculator screen at some point, 10 times the sine of 63, which is approximately this in centimeters. How is that helpful? Well, if I look here now, I know this line is approximately 8.91 centimeters. Well, now if I look at this triangle that has LM in it, remember, like I mentioned before, this must be a 90-degree angle. So if I look at this triangle, I know this line KM. I also can figure out this angle right here quite quickly, because all I need is one of these angles. And there's always more than one approach. I'm going to find angle L. And that's because if I look at this big triangle, triangle K, not K anything, triangle JLM, if I look at that triangle, I know there's 63-degree angle right here. I know it's a 90-degree angle here. And I know that the interior angles of all triangles always add to 180, which means a quick little bit of subtraction from 180 of 90 and 63 leads me to 27 degrees. So I know this angle up here must be 27 degrees. And now from that angle, I know the side opposite to it. And from that angle, I'm trying to find the side that is the hypotenuse. Because again, this side right here we're trying to find is the hypotenuse. And I know that because here's my right triangle, and the hypotenuse is always opposite the right triangle. Because keep in mind, at this point, I can ignore, in fact, I will temporarily do this. I will obliterate this triangle at the bottom. If I get rid of this triangle at the bottom, it makes it more clear that the side we're trying to find, LM, is the hypotenuse. The hard part is not getting distracted by all this stuff down here. And so let me clean this up a little bit. But looking at triangle LKM, I'm trying to find the hypotenuse. I know the side opposite, 27 degrees, so again, I want to use the sine ratio. And so the sine of 27 degrees is equal to opposite, which is 8.9100, divided by the side we're trying to figure out, which is LM, the hypotenuse. And so at this point, anytime we have our unknown is in the denominator, it's the same as LM equaling 8.91 divided by the sine of 27. I'm doing that quite quickly because these are things we've learned in grade 10. And go to my calculator, and LM is approximately 19.6 centimeters if we round to one decimal place. Other options quickly to solve this is we didn't really have to find that 27-degree angle up there. Another option is once I know this is 63 and I know this was 90, I could have realized that this angle right here must be 27 degrees. And then I could have subtracted that from 90 to find this angle right here. In the end, there's always various options, but I'm not going to make this more time consuming than it has to. All right, the last question, I don't even have a triangle. I have this quadrilateral in which there's no 90-degree angles at all. And we want to find the area of the entire shape. The key is, if I cut this in half in any way I want, I'm going to cut it in half like this. I now have two triangles, neither of which are right triangles, but I can find the area of each of these triangles separately. This triangle here and this triangle here, I can find the areas of them quite quickly. I'll call this A1, I'll call this A2, using what I have in my key ideas here. Remember right here, I can find the area of any triangle if I know two sides, A and B in this case, and the angle in between them. Well, that's what we have right here. If I look at triangle A1, the one in yellow, I know two sides as well as the angle in between them. And the same idea down here. I know two sides as well as the angle in between them. And so I can use those then to find the area of these two triangles and then add them up. So for example, let me just write down the basic formula now. Which, keep in mind, in itself, we got to realize what all these things stand for. So again, AB are two sides that are adjacent to one another, and the sine of C being the angle between those two sides. So looking at angle 1, I'll put A1 equals 1/2. So my two sides, I got 63.2 and 36.1 times the sine of angle C, the angle between those two sides. That's 75 degrees right there. Now, that said, I can find that, or I can just realize I don't really care about that number, no offense to it. I want to add it to the other one, so I want to add this to A2, which is 1/2. This is going to be, looking at the triangle in green, it's going to be 1/2 44.7 times 60.8 times the angle, the sine of the angle between them, which is 73 degrees. So everything you see highlighted in yellow applies to A1, everything highlighted in green applies to A2. And while I could work these out separately, in some ways you may be better off just typing this all in one go in your calculator and just let it, so you don't have to worry about missing anything when rounding. And put this all together and you get approximately 2,401 square meters. I'll round to the nearest whole number. We're dealing with such a large landmass here that it's meaningless to get really picky about small values, decimals of square meters. And so that's what I'm looking for there, roughly 2,400 square meters. Keep in mind, if you did the same thing this way, but you broke them up on this diagonal, our work would be different, but you would get essentially the same answer. It wouldn't be exactly the same because actually everything here is rounding. All measurements are, any real measurement is rounded. There's no such thing as a perfect measurement. And so if you did it the other way, you would get essentially the same answer. But it wouldn't, if you look at all the picky decimals, it wouldn't be exactly the same. But who cares again? It's about 2,400 square meters, and then we're all happy with that.